Ladies and gentlemen, we're going to do 7.3. We're going to be talking about our volumes of solids of revolution, and we're going to talk about specifically the shell method. All right, so our objectives say exactly the same thing, slightly different, image than we've had previously. Notice that here's my axis of revolution, and I have a shell, so it's kind of like our donut problem, except the hole runs all the way through, and I'm revolving this. Notice that if this is my axis of revolution, the rectangle that we always draw, so this would be a delta y in this particular case, notice that my rectangle is parallel to the axis of revolution, which is very significant to the shell method because it's different than the other methods that we've talked about so far. This is the height of our rectangle. W would be the width of the shell, so that would be the width of my shell. So put a little W there. P is the distance from the axis of revolution to the center of the rectangle. The outer radius would be P plus. So P would be from the axis up here, right? So that would be W divided by 2, and then the inner radius would be P minus W over 2. And I'm just going to show you how this formula, was kind of derived, and then we'll simplify it and put it in a form that we can remember when we use. So it says that the volume of the shell, and I like to think about like clay pipe or a PVC pipe because it has a thickness, but it's still a type of pipe. So that's what I tend to think of when I think of an outer and an inner radius. Okay, the volume of the shell is going to be the volume of the cylinder minus the volume of the hole, which is kind of what we've talked about in our previous videos, where this is the volume of the hole minus the volume of the hole. And so if we talk about our whole cylinder, it's going to be pi r squared h. And then if we talk about the volume of the hole, it's going to be pi r squared h. Okay? Well, then if we put in our radii, so this is going to be pi times, and this is my outer radius, P plus W over 2 quantity squared times H, minus pi times my P minus W over 2 quantity squared times H. I could factor, and I would come up with 2 pi times P times H times W, which is basically the formula that we're going to use when we put it into integral notation, but this is going to be 2 pi times the average radius, which was dividing by 2 to get the average, and then it's going to be the height, and then it's going to be the thickness. Alrighty? So again, one of the things that's really important to remember about the shell method is that the rectangle that we typically draw is going to be parallel to the axis of revolution instead of perpendicular to it like our other ones have been. And so then, let me go to a new sheet of paper just so I can draw some pictures. If I have a horizontal axis of revolution, and I'm going to draw a little picture. So let's say here's my first quadrant, and maybe let's say I have some curve, right? So then the height is going to be here. So this is going to be the height of my, let me draw my little rectangle in here like this, okay? So if I have a horizontal axis, so that means that my rotation is happening maybe about our x-axis, then this is going to be my delta y. The height is going to be h of y, and then the distance from the axis of revolution up to here is going to be called p of y, which for almost all intents and purposes will be y. So then if I write my volume formula, sorry, it's going to be 2 pi, and it's going to be times the integral from c to d. Notice because I have a delta y, everything needs to be in terms of um, y. Sorry, brain fart. And then I'm going to have the distance from the axis of revolution to the center or to the rectangle. And then I'm going to have times the height of the rectangle times the thickness of the rectangle. Okay? Alrighty. And then if I have a vertical axis of revolution, sorry, I'm really hoarse today. All right, if I draw my handy dandy little axes and draw my cute little curve, and this time I want to rotate it about the vertical axis, then my rectangle, my representative rectangle, needs to be parallel to the axis of rotation. This is going to be a delta x. This is going to be, so it's the distance from the axis of revolution to the rectangle, so this is going to be p of x. Sorry, we're just going to call that distance x. And then this is going to be the height of my rectangle, and we're going to call him h of x. So the volume would still be 2 pi. Now I would integrate from a to b, and I would have p of x times h of x dx. So those are the basic formulas. The key thing to remember when when I'm doing the shell method is that the rectangles that I like to think about, they have to be parallel to the axis of rotation. So let's do an example. I want to find the volume of the solid of revolution, because all our problems have said the same basic intro, formed by revolving the region bounded by y is equal to, hang on, I need to shoot my paper up so you can see what I'm doing. I have x minus x cubed, and then I'm going to have the x-axis, and then I'm going to have 0 is less than or equal to x is less than or equal to 1, and I want to rotate this little guy about the y-axis, okay? So I'm going to draw a picture, because I like pictures. I usually need things to help my poor little pea brain. So I'm going to have my curve, and I'm going to make it kind of exaggerated just so we can see everything. This point of intersection would be 1, 0. Here's going to be my representative rectangle. So notice that I have a delta x, which is parallel to my axis of rotation. Okay, this is the point 0, 0, so we'll make my dot big so it looks like my graph is good. Okay, the height of my rectangle, h of x, is going to equal x minus x cubed, and then this distance from the axis to the rectangle is going to be x, and then this is my p of x. So then my volume is 2 pi. Because everything's in terms of x, I'm going to go with my horizontal. So I'm going to integrate from 0 to 1. My p of x is x. My h of x is x minus x cubed. And then I have dx. So remember, in case you need it, this is p of x. This is the distance from the axis of rotation to the rectangle. Then this is the height of the rectangle. And then this is the thickness of the rectangle. So then if I do this math, I'm just going to get 2 pi. I'm going to integrate it from 0 to 1 of x squared minus x to the 4th dx. Miraculous math happens. And this would be 4 pi over 15. And then you would write your conclusion statement and make it all nice and pretty. So that is our shell method. And in that one, we rotated it about the y. Okay, so I have another example. Of course, I have another example because I always have lots of those little guys. I want to find the volume of the solid of revolution. Whew, that's a lot of words to have to write. Formed by revolving the region bounded by, and then we're going to have the graph, kind of cool looking. X is equal to e to the negative y squared. This should be a hint because it's in terms of x. We're going to have the y-axis, and then I'm going to have 0 is less than or equal to y is less than or equal to 1, and I want to go about the x-axis. Okay? Well, because my equation is already in terms of x, this makes sense because that means I'm going to have a delta y. So if I were to graph this little guy, it's going to be kind of a crappy graph, so sorry. It would look kind of like this. This is 0. This would be from 1. These are my y restrictions. And I'm rotating about the x-axis, which means my rectangle, sorry, that's what happens when you go mule riding out in parks in the wind. Oops, my bad. He's a delta y, okay? And then the height of my little guy is going to be h of y is e to the negative y squared, okay? And then my distance to the rectangle from the axis of revolution, right? Because this is my axis of revolution. My rectangle is parallel to the axis. This distance is going to be y. So that when I set up my integral, my volume is going to equal 2 pi. And then I'm going to integrate from 0 to 1, p of y, h of y, dy. So here's the 2 pi. 0 to 1, p of y, the distance is y, and then my h of y was e to the negative y squared dy. And remember that the integral of e to the y is e to the y. Remember that the derivative of e to the y is e to the y. It's kind of a handy-dandy all-purpose little equation. If I did use substitution, then I might let my u equal the negative y squared, so my du would be a negative 2y dy. And so then if I finish the problem, I would have to introduce a negative 2 on the inside, and I would introduce a negative 1/2 out here. So I'll do it in a different color. I'm going to put my negative 2 in here, and I'm going to put my negative 2 in the denominator out there so they counteract each other. And then I end up with a negative pi integral from 0 to 1 of e to the u du. And then if you were to finish your problem in all of your brilliance, you would get that the volume is equal to 1.986. And you could do this either with u substitution, or if you were lucky enough for it to be on the calculator portion of your test, you could just do it in your grapher. So the next thing that I want to do for you is I want to compare. So I want to do a comparison of the disk and the shell methods, because they're really quite similar, but at the same time they're fairly different. So in the disk method, remember that my rectangle is rotating and creating a circle. The rectangle is going to be perpendicular to the axis of revolution. And then, since we just talked about it, I'll put my shell method over here. Remember, in the shell method, the rectangle, and I think you know which rectangle I'm talking about. So I'm talking about the rectangle that determines my dy or my dx. My rectangle is parallel to the axis of revolution. So that's the primary difference between the two. Well, I guess there's several differences, but these are the two significant differences. So then if I draw a picture, so let's say I have some random curve, and I draw my little rectangle, okay? In the disk method, my rectangle is perpendicular to the axis of revolution, which means that this is going to be my axis of revolution. This is a delta x. This distance is the height of the rectangle, and we call it r of x. Also the radius of the disk, right? So as I revolve this disk about the x-axis, it's going to be the radius of the disk. So the volume, and so let's say we go from A to B, is going to equal pi, because remember that the area of a circle is pi r squared. Alrighty. So when I write my integral, it's going to be from A to B, and then I'm going to have r of x quantity squared minus my little r of x quantity squared, and then I have my dx. Okay? So remember, this is the area of the whole minus the area of the whole, and then that would be the disk method. So if I take the same situation and if I consider the shell method, and if I'm rotating about the x-axis, that means that my little rectangle has to be parallel to my axis, which means that this is delta y. And remember that p is the distance from the axis of revolution to your rectangle, so this distance is going to be y, and then this would be the height of my rectangle, h of y. And I'm going to put p of y out here just so we remember. Okay, and so then I have my integral from a to b. Okay, so then my volume, if I'm using the shell method, is 2 pi. And then I'm going to integrate from A to B. I'm going to have the distance y times h of y. I'm going to do h of y, and then I have my dy. And since I have a dy, everything has to be in terms of y, so that's a great way to check your work. All right, I have one last example for us, and then a little quick recap, which is nice because we haven't been going for too long yet. So I want to find the volume of the solid. So I'm going to find the volume of the solid by revolving the region bound by the graph of, and then I'm going to have y is equal to x cubed plus x plus 1. Y equals 1, x is equal to 1, and I want it to be about, which means that's going to be my axis of revolution, the line x is equal to 2. So I'm going to draw this one, okay, just to give us a sketch. All right, so here's my first quadrant, and I have y equals x cubed plus x plus 1, which is going to look kind of like this. And then I'm going to have the line y equals 1, and it's going to be here. We'll put it here. So this is f of x. This is y is equal to 1. And then I have 1, 2, and I'm going to label my x-axis so you know which axis I'm talking about, and my y-axis. And then I'm going to go x is equal to 1, which is this line right here. And I'm going to draw it in a different color. I'm going to draw my axis of revolution. That's the center line in drafting, by the way. So then this is the image that I am going to rotate about this. So you could probably do either method, but I think at this point the shell method is probably easiest. So I'm going to draw my rectangle parallel to my axis of revolution, and this is going to be my delta x, okay? Because notice that my image is bound and it's right in here, and I'm rotating it here, so I have a hole here, okay? So my h of x is going to be the height of the rectangle, and it is going to be the top minus the bottom. Oops, except bottom has an m in it and not a w. And that's going to be the x cubed plus x plus 1, and then my bottom is the minus 1. So that means that my h of x is going to be x cubed plus x, okay? So the next thing I want to find is my P of x, and remember P is the distance from the rectangle to the axis. So this is where it gets a little bit entertaining. So this is my distance x, and then this is my axis of revolution. So if I want to find, let me use this color. If I want to find this distance, so the distance from the rectangle to the axis of revolution, then P of x is going to equal the axis minus x, and then that would give me this distance in here. Okay, so it is the distance to the axis minus this distance, and then that would give me the distance from the rectangle to the axis of revolution. Okay. What else do I need to write? I have my delta x, I have my P of x, I have my h of x, so I just need to write my integral. So my integral is going to be 2 pi. You also have to remember when to use a singular pi and when to use 2 pi. And I'm integrating from 0 to 1, which is this little information right in here, okay? And my graph is actually kind of crappy because it kind of comes up this way. Sorry, I was just looking at that. So my graph would be over here looking kind of like that. And then I have my P of x, so that's going to be the 2 minus x. And then I have my h of x, which is x cubed plus x. And then all of this is dx. And so the hardest part on this is getting it all set up. The actual act of integration is fairly straightforward. And then if you did all that miraculous math, I'm going to get 29 pi over 15, and that would be the volume of my revolved solid. All right, so the last thing that I want to do is kind of recap what we have done so far with our revolved solids. So this is going to be a recap about our revolved solids. And I'm going to talk about the 3 different methods. All right, so in the disk method, which was the first method that we got, remember that if I have a curve and I draw a disk, right, so this would be my delta x, my rectangle is perpendicular to the axis of revolution, so the volume would be pi, because when I rotate this about the axis, it creates a disk. The area of a circle is pi r squared. The volume is the area of the circle times the thickness. So then I'm going to integrate from a to b, and then I would have r of x quantity squared dx. So that was the first one that we learned. The second one is when we start introducing holes and creating a bit of a problem child, right? So my volume is going to be, it's still a disk, but now it has a hole in it, which is why we call it a washer. And then it's going to be from A to B of the whole squared minus the whole squared dx. So this is the whole minus the whole. And that helps me greatly when I'm thinking about what's my whole going to be and what's my little whole going to be. And remember that if I'm going with a dx, that means that I'm going top minus the bottom. Okay? And then if I wanted to do a dy, then I would do right minus left. And then the last method that we studied was the shell method. This one is the one that is unique because if I have a shape and I'm rotating, say, about the x-axis, then that means that my rectangle is parallel to the axis. So in this case, even though we're rotating all 3 images about the x-axis, now I have a delta y, which means all of my integration stuff, my antiderivative, has to be in terms of y. So my volume is 2 pi, and then I have from A to B, P of y, which is the distance from the rectangle to the axis of revolution, times H of y, which is the height. So this is the height of the rectangle, and then I have dy, which is the thickness. Alrighty, that covers the 3 things that we have done so far with our revolved solids. I will see you soon.